Okay, hello everyone. So today we're going to be talking about predictions and modeling. And here's an overview of where we've been. So we are right here. We're ready to start. Yeah, so just this is going to be the last lesson before ANOVA. In this unit, we've already talked about hypothesis testing from one sample. We've talked about two sample tests, chi-squared tests. We've also talked about correlation. Now we're going to use what we know about correlation to be able to talk about regression and prediction, or modeling and prediction. Okay, the goals of this lesson are to review equation of a line and to find the line of best fit and its properties, the line of best fit for data. Then we're going to use the line of best fit to make predictions. Okay, so in our review, let's start with the equation for a line, which is y equals mx plus b. All right, so this should seem familiar to us. This m here is the slope of the line. This b is called the intercept. And the graph of the line is the set of all points that satisfy this equation, okay? The set of all points that make that equation true. So, for example, if we have y equals 2x minus 3, if I plug in x equals 0, what do I get out for y? Y equals, well, 2 times 0 is 0, minus 3 is negative 3. And so that's that point right there. That's my starting point. Now I could have just gone straight there because that's my intercept, which is always where the graph intercepts the y-axis. Well, where do I go from there? Well, my slope is going to tell me. So slope is, if my x increases by 1, my y value is going to increase by m. See, if we instead have x plus 1, my y is going to be added on, increased by m. And so what that means is that since my m is 2 here, I'm going to increase by 2. Another way to think about this is to recall that m equals the rise, or the change in y, over run. So that's change in y over change in x. And so, in our example, 2 is the same thing as 2 over 1. So that means it rises 2 as it runs 1. And so there's my line. Okay. So you'll recall that before we're working with a scatter plot. And when a correlation is suspected, we would like to try and predict one of the variables, the response variable, given the explanatory or predictor variable. So that goes back to what I said before. Correlation correlation means that one variable gives you information about the other. Now, this is called prediction, or sometimes just estimation. The way we do this is we use what's called the line of best fit, which is also as we'll see more of, we'll see this is the least squares regression line. And it's the equation of a line. So here's my slope. B1 is my slope. B0 is my intercept. Where do we find these values? Well, as it turns out, the slope of the regression line is always going to be r times the standard deviation of y divided by and that's your B1. Once you have B1, then you can compute the mean of y and the mean of x. So the mean of your y variables and the mean of your x variables. And once you do that, you can then form your intercept, which is B0. Now, once you have that line and you have some data that you're trying to predict, you can use this line. So you plug in x tilde for x, and you get out y hat. That hat is the notation we use for something that is estimated. And the tilde is sometimes used to represent data. So you might not have data for y, but if you have data for x, you can determine what y is most likely to be. Now notice what happens if there is no correlation. If no correlation, then r is going to be basically 0, which means that B1 is basically 0. And if B1 is basically 0, then B0 is basically y hat, the average of y. And so that means that your best prediction of y for any x is going to be this B naught, which equals y bar. So the best approximation of y is the mean of y when no information from x can be obtained. And so no correlation means no information from x. if there is a correlation, then you will have some slope, either positive or negative, and that slope is r. And that slope is b1, or r times the quotient of the standard deviations. Now, what you can do is you can take that line, you can plot it, and it's always going to go right through the middle of your data, like this line does. It goes right through there. And so when we are using the line of best fit to estimate a y value, it's always going to land right on that line. So, for instance, if I had somebody that was 242 pounds, their y value, their height, is going to be, somewhere over here, like 82, maybe 82 inches. And that's, given the data, that's our best guess of their height, given that they weighed 242 pounds. So this here is going to be my y hat. This here would be my x tilde, and that's how I approximate y, the weight. Okay. Now, there's something called the residual plot, and with that, those are the errors. So for all of the data that we have a y, and we also have a predicted value, which is this value on the line of best fit. So for instance, let's take this data point right here. That's an actual data point, and it differs from what the prediction would be, which is down here on the line of best fit. This difference here is the error of our prediction. And we're pretty much always going to have some sort of predictive error. And that's mainly because our data is generally noisy or depends on things other than what the x value is. This error is also known as the residual. These residuals by themselves can be plotted. So it's difficult to see, but this plot right here is a plot of only the residuals of our height and weight linear fit, our line of best fit. But you may be convinced. So these 2 points here, for instance, correspond to these 2 points. The reason one is lower than the other is because since my line is sloped, the difference between this line and this line is smaller. So on this plot, I am plotting the vertical distance from line of best fit. This point right here is below the line of best fit, and so on our residual plot, it's going to be negative. You look at these 2 points here, those are represented right here in my in my residual plot. Okay, now as it turns out, the formula that I gave you for the line of best fit is a special formula in that it satisfies what's known as the least squares property. Well, what does that mean? Well, if you were to take the residuals and you were to make a square, so you have this data, right? And you have your line of best fit, and your residual is the difference between your data and the line of best fit. Well, if you take that difference and you square it for every single point, you're going to get a bunch of squares. If you find the area of all of those squares together, the line that I gave you will minimize that quantity. So, for instance, you've got this one. Suppose we wanted this line here to be a line of best fit. Is this a line of best fit, we're wondering? Well, no, I don't think so, because look at how big these residuals are. And if you were to square the residuals, these would all be very, very big. So that is a bad choice of the line of best fit. It does not satisfy the least squares property. But our line of best fit is guaranteed to satisfy the least squares property. And so our line of best fit that I just gave you from above is guaranteed to satisfy the least squares property, meaning it is the line that has the smallest sum of these residual squares here. And so that's a good way to find a line that goes right through the middle in an optimal way. Okay, let's think about the interpretation of r squared. So we observe that our prediction here is b1x times b0. Now what if we were to compute, say, the mean of y, or the mean of y hat? That is going to equal, if I take all the So if I take the sum of all my y hats, divide them by n, that's going to be the same thing as b1. I can factor out of my sum and these constants here are just going to add up. I'm going to have n of those b naughts, but I'm dividing by n, and so I end up getting b1 times mu x plus b naught. Now, if I were to find the standard deviation of y hat squared, that is going to be the sum of my the sum of my y hat squared minus minus mu of y hat. And mu is a little bit of abusive notation because it is a form of data. We should do y hat bar, but I don't want to do y hat bar, so I'm just going to use mu. And so what this comes out to is my b naughts cancel, and I can factor out my b1, and I end up getting just b1 squared. It's squared because I'm squaring everything, times sx squared. And so that's how we get that equation right there. Now remember that b1 equals r times sy over sx. And so b1 squared is r squared sy squared over sx squared. That's b1 squared. If I multiply by sx squared, then I just get r squared s squared y. So the variance predicted by the x variable, so this right here, if there's any variation, it's entirely from the x variable, because this is just a function since y hat is completely determined by x. So y hat represents the area, the variance predicted by the x variable. That is this proportion, remember r squared is going to be less than 1, so it's some proportion of the variance of y. And so one way of saying that is that is that the variance predicted by the x variable is a full x squared of the actual variance of the y variable. So there's some noise or variance that's unique to y, but the proportion that is the proportion of that variation of y that is, we say, explained by x, that proportion is r squared. So that tells you how much of that variation in y can be contributed to the variation in x. Okay, now, there's two different ways you can fill in values when you have a line of best fit. One, you can do what's called interpolation. And that's when you have your data and you have your line of best fit, and you're curious about a particular value inside of the range where your data is. See, so the range of data is like here, I've got x values for that. That's called interpolation. Interpolation is using the linear model. So this right here is a model for y in terms of x. A model to predict y values inside of known data points. On the other hand, extrapolation is using the linear model to predict values outside of known data points. So that would be using this linear approximation to approximate this blue point here. So I have a x value that I want to find the y value of, and so I plug it into my linear model, and I get some y value out here. This is called extrapolation because I am doing it outside of the data that I have. Now that is a risky process because you don't know how far after your data these x values are going to follow this linear regression line, or if they even make sense. Generally speaking, if we do have a linear correlation, it may not last for very long. It may only apply to the data that you've the range that the data falls in. And so here's some examples of where that might be problematic. So that's the danger of extrapolation. Sometimes extrapolation is a good thing, but it needs to be done with care. Okay, let's go ahead now and take an example, and let's use our regression line to predict the stopping time for a car going 21 miles per hour. So we're going to use the same data that we did before, data from the 1920s about the car stopping time. Okay, I have here my sheet from day 22. We're just going to add to it. So first thing I'm going to do is I'm going to get my line of best fit. Notice that we have already seen that there is a statistically significant linear correlation. And so the next thing to do would be to plot the line of best fit. We start with B1, and that is just going to equal, well, let's see, I need a few things here. I'm going to need R, I'm going to need SX, and I'm going to need XY. SY. Okay, so R is a correlation that we found from before. So I'm just going to go ahead and retype that in. So that's correl. Get my first array here. And my second array. Here we go. There. All right, good. So there's my two arrays. Enter. There's my R. And that matches the same R I found before, right there. Okay, now I need SX and XY. And so I'm going to do equals stdev.s. There it is. I'm going to go ahead and select this. Get down to there. All right, enter. There's my standard deviation for my X variables. Or my explanatory variable. And then I'm going to find the standard deviation for the other variable, for my response variable. stdev.s. All right, there we go. And so B1 is going to equal R times SY divided by SX. Okay, how do I know it's SY over SX? Think about slope. This is the slope, right? Change in Y over change in X. So the standard deviation in Y goes over the standard deviation of X. Press enter. There's my slope for the line of best fit. Now I would like to find my Y, my intercept, B0. Well, in order to do that, I need B1, which I already have, but I also need X bar and Y bar. And so right now I'm gonna take the mean of my data. So this thing's gonna equal average. There I take the mean of the speeds. And then I take the average of the stopping times. And so now B naught is going to equal y bar minus B1 times x bar, enter. And there's my intercept. Okay, let's go ahead now and come up with my model and my predictions. So that's this. I'm going to call this, oh, sorry, not stopping time, stopping distance. So this is going to be my predicted distance. That is going to equal B1 times the speed plus the intercept, B naught. And I'm going to fill down, so I want to put some dollar signs there and right there. Okay, we see that? Enter. Now I'm going to go ahead and fill it down. All right. Okay, now what I want to do is I want to plot these. And so I think one thing I can do is increase the plot area. All right, how did I do that? So I just selected my plot. So it was like this, right? There's my plot. I selected my plot so that I saw the the data that was being used is highlighted. And you'll see there are those dots in the corner. I clicked and dragged on the left dot, on the right dot, the right side dot, and I dragged it to include my predicted dists. And when like that, it automatically made it orange, and I look at my scatter plot, and there is the predicted. The predicteds are the orange points. And so that's my line of best fit. Okay, now what the question wants me to do is to use this to predict the stopping time, but that should say distance. Associated with 21 miles per hour. And so what I'm going to do is I'm going to put this little point in here, 21. Oops, sorry. Put that right here, 21. And then I'm just going to drag this, or copy, paste that value right there. So notice what it's doing. It's doing exactly what I need it to. It's going to take my B1 and multiply it by the 21, which is in the red square, the red cell, and then it's going to add my intercept. And so that gives me my predicted distance. That's how far it's going to go before it comes to a complete stop. 65. Okay, and so that would be my answer. Another way of writing this would be to report the B1 and the B naught. Let's go ahead and grab that. So I have taken a screenshot and I'm getting all the information that I need here. So I have my B1 and my B0. Okay, done. Copy and delete. Come over here. Paste. So there's the information for my line of best fit. Of course, I don't need it here. Okay, and so here's the information for my line of best fit. And so I've got y hat equals 3.9324. Let's see, that's a bit too much. Let's just go one more than what the data was given. Times x, which is my speed, minus 17.6. Okay. And so we have 65 is about 3.9 times 21 minus 17.6. That's what I got from Excel. I remembered it. Okay, now a few things. If x is below a certain value, then your stopping distance is going to be negative. Well, that doesn't make sense. So this has a limited range of usefulness. So what would that be? So if x was a little bit more than 5, if x were less than 4, certainly, then this would not make sense. Because you can't have, if you were going 4 miles an hour, it doesn't make sense that it'll take you a negative distance to stop. So this model is not valid. It's valid within the range that it was designed for. So it's valid within the range it's designed for, but clearly not valid outside of that range. And so this 21 here, this is interpolating. Because it was comfortably within the range of x values. Okay, let's go back to Neptune and burglaries. And so again, it asks us, let's see, does there appear to be any correlation between the data? And there appears to be a statistical correlation between the data. And so, if so, find the linear model relating the distance the Earth is from Neptune and the rate of burglaries. So the x value, the explanatory variable is usually the first one, and the response variable is usually the second one. So about what burglary rate would you expect in 2025? When? And then also it gives us this right here. So that tells me that Neptune is the input variable, or the explanatory variable. So this will be my x. Okay. All right, let's see what I can copy and paste from my previous slide. Copy that. Command C. Come back over here. Command V. All right. So let's see what we have. So that all looks good for B1. My regression, oh, okay, so I've got to fix this range right here. Okay, so let me get this range up here. Distance from Neptune. Eight to 45. Look at that, 8 to 45. I'm just going to do that. This is going to be C8 to C45. All right, enter. There's my correlation. Same correlation as what we saw before. Right there. All right, now for this one, the x's are the B8 to 45, so I'm going to write that. B8 to B45. Okay, then this one, whoops. This one's going to be C8 to C45. Oops, it doesn't like my asterisks. 8. Okay, good. Now this one. Now that looks okay. We're just missing these. So this one needs to go to B8 to B45. Doesn't have to be capital. And then this one is going to be C8 to C45. Enter. All right, so let's go ahead and take a look. So this is going to be my predicted burglaries. And it is going to equal my slope, which is right there. So look at that slope, 2,881. That means that for each unit of distance, which is astronomical units, burglaries increase by 2,880 per 100, whatever that rate is. All right, so I've got my slope times the distance plus B naught. And I'm going to put in my dollar signs now. Hold those the same. Oopsies. Okay. There. All right, let's see. Okay, what happened? That looks good. Oh, look at B. I want this to be F. Okay. F. All right. Let's take a look. Let me make sure it's referencing the right cells. Yeah, that looks good, and the dollar signs are in place. Okay, I'm going to go ahead and fill. I'm going to fill down. There it is. Okay, very good. Now for the real test, I'm going to click on my plot, and I'm going to drag my data Okay, I'm gonna Whoops, okay. Click on my plot. All right, it doesn't seem to be working. So in that case, what I'm going to do is I'm going to delete my plot, and I'm going to select all of this data. And I'm just really going to hope that it's going to put the distances as the x values and those other two columns as the other y values. Insert chart, scatter plot, right there. Looks like I got lucky and Excel did exactly what I wanted it to do. This rarely happens, but it happened today. So you can see that the orange ones, again, are a very good approximation of the blue ones, of the data. Okay, now what was asked of us? We were to find what distance I would expect when Neptune is 29.9034 astronomical units away. So I'm going to put that one down right here. 29.9034, I think is what it was. Yeah. All right, and then I'm going to copy, Command C, copy this formula, Command V. There it is. Let me just look. Yep, it's referencing all the right stuff. And so that's going to be my value there. Now I wonder if I can extend this. I wonder what happens if I go like that. There, that point right there, I don't know if we can see this. This point here is my new point. It doesn't have a blue point associated with it. This is extrapolating. I've extrapolated beyond the range of data. All right. Okay, let's go ahead and do the same thing we did before. Let's grab this information right here. With a screenshot, actually. Let's just take this whole thing. Let's take line of best fit. Let's take that whole plot as well. Done. Copy and delete. Go back to Notability. Throw that right there. All right. And so, my data, my line of best fit is going to be y hat, which is my distance, predicted distance. No, sorry, burglaries is going to equal 2,881.6353. Let's go 4 decimal places because I think astronomical units was 4 decimal places. Well, now this is actually something that's being multiplied in by y. So what are the units? How many decimal places is the data for y? Let's take a look. Go to Excel. Y is to the nearest 10th. So if y is to the nearest 10th, then we'll just make this to the nearest 10th as well. Okay, so about like that. Times x plus, no, minus 85,855.3. Okay, and so that right there is my line of best fit. And when I use it to find when x equals 29.9035, I found that y hat, my predicted number of burglaries, is 315. Let's just check on that number again. Yep. 315.4. 0.4 burglaries. Per, it's some sort of rate. Okay, what did we do today? Well, we talked about the line of best fit. This is a we talked about an interpretation we talked about linear model. We talked about an interpretation for r squared. And we talked about interpolation and extrapolation. I'll just say one more thing about this x squared. So going back to this, Neptune example, we look and we see that, there's some variation in what x equals. And we'll talk about the variation thing in class. All right, and that's pretty much it. Okay, everybody, have a wonderful day, and we'll see you later. Thank you.